So before I talk about this third important class of examples, affine vertex algebras, I want to finish off what I was talking about last time, the construction of the lattice vertex algebras. So remember, the idea was we were trying to construct a vertex algebra structure on this direct sum of modules over the Heisenberg vertex algebra. Okay, and we discovered that, the vertex operators associated to these vectors mu have to have this very specific, very complicated form, okay? So basically what's left to do is to figure out what these coefficients have to be, okay? So to do this, the first thing I want to do is to rewrite the thing slightly to facilitate. So I'll just do a sort of formal change of notation here. Multiply h beta by a one-dimensional vector space with a basis that I'll call E beta. Now I do this because, so now I want to rewrite this operation u to the mu as e to the mu, okay? So this is now an abusive notation. What I'm really doing is I want to think of this operation u to the mu as multiplying e to the beta with e to the mu, okay? Okay, so this is the idea. It's just a change of notation so that I can absorb these factors, c mu beta, into the structure constants of some algebra, just given by multiplying these formal exponentials. So you take the group algebra of the integers, and then we twist it. So we redefine the multiplication to be like this. So the final step is to derive consequences of locality between these fields gamma, which we haven't used yet. So it's a bit of a complicated computation, but I'll just summarize the results. So kind of a key part of this so what you have to do is you have gamma alpha and a gamma beta, and you multiply them, with z and w as variables, multiply them in one order, multiply them in the other order, and subtract, and the result has to be annihilated by some sufficiently high power of z minus w, this definition of locality. So to do this computation, one of the key sub-computations is the following. So there's an exercise to do this computation. And using that, we see that if we multiply gamma mu of z with gamma of beta, then we get well, maybe I'll just say a bunch of stuff. And if we multiply in the other order, yeah, I can be slightly more specific. So we find this product is equal to this factor multiplied by the normally ordered product. And if we multiply in the other order, we get basically the same thing, the same normally ordered product with the other expansion of this term here. So, well, long story short, in order to get locality, we just have to make sure that when we multiply these two terms in one order or the other, the difference is a minus sign. or in other words, that C beta mu has to be equal to C mu beta multiplied by a minus 1 that comes from this term, minus 1 to the mu beta. Okay, so anyway, we get a relation between these two coefficients. If this is for all mu and beta in Z. So if we take mu equal to beta equal to 1, then we get that C11 must be equal to minus C11. So, yeah, actually the conclusion is that there is no vertex algebra structure on V. So, end of story. What you could do, though, it's apparently bad news. What you could do is take just the even integers inside the set of all integers, right? And then in this case, yeah, this factor minus 1 to the mu beta is 1 for all mu and beta, so just taking C to be trivial, C equal to 1, does the trick. Okay? So we do get a vertex algebra in this case. Now, it's possible to salvage V as well. The point is, what happens is you don't quite get a vertex algebra, you get something called a vertex superalgebra. And I don't want to, I mean, those who know about superspaces will know what I'm talking about. Those who don't, I don't want to give much of a lesson on vector superspaces, but somehow the idea is like a vector superspace is formally a direct sum of two vector spaces, one of which you call even, the other you call odd. Then you define like associative superalgebras, least superalgebras, etc. Basically by taking usual relations for purely even objects and then inserting these minus signs whenever you want to commute or exchange the order of two odd elements. So there's this whole notion of superalgebra, and in particular the vertex superalgebras, in which locality, usual locality should be replaced by, if you have two fields associated to odd elements, then call them A and B, then A of Z, B of W plus B of Z, B of W, A of Z should be annihilated by some sufficiently high power of Z minus W. So in this case, so let me write some of this. Okay, so now as the name suggests, lattice vertex superalgebra. So this is a special case of a much more general construction, wherein you can associate a vertex superalgebra to any so-called integral lattice. So first let me say exactly what I mean by an integral lattice. Which I'll call L, of finite rank. Together with a bilinear form from L times L with values in Z. Okay, and we call a lattice even if the squared norm of any element is even. Okay, so this is the case for 2Z, it's not the case for Z. So an example is this triangular lattice called A2, which is the root lattice of the algebra SL3. So here, like here's 0. And here's a basis for the lattice, alpha and beta. And alpha alpha and beta beta is 2. So you can deduce that lattice is even. And just to be careful that being even doesn't necessarily mean that all the inner products are even integers. Product between alpha and beta is -1. Okay, so the ambient space, by which I mean not R2 really, I mean the complexified ambient space. Inherits this bilinear form by linearity. And then using this H, we'll form a Heisenberg vertex algebra like before, like I said at the beginning of the first lecture. now that we have more notation involved, so you can check that if you write H for this element in the vertex algebra, which identifies, so H is an element in H, which I can then identify as a subspace in H of H in this way. Anyway, these elements generate the vertex algebra in the same way that occurred in the first lecture. And you can check that the OPE for two of these guys is just given by this scalar multiplied by lambda. Okay? Not sure why I recalled that relation, because I'm not going to use it. But anyway, the construction now is to use the lattice to produce a vertex algebra. On the space I'll call VL. And recall that we had modules over H of H for each alpha in in H. So we'll take this discrete sum of those over the lattice and build some vertex superalgebra structure on that. Okay. In general, the problem of finding such a function is a little bit more interesting than it was in the one-dimensional case. Because in the one-dimensional case, both for 2z and for z, we found we just took the function 1 and it worked. But in general, say for A2 lattice, I mean, every vector has even norm, but you do have pairs of vectors that have odd pairing. And so you really do have to introduce some non-trivial function to get this to work. You can always do this, but I won't prove why. Okay? So now let me switch gears slightly, but I'll soon come back to this. So in the second lecture, we saw this so-called Borcherd's identity, which was written out as an expression involving fields. And so in this exercise, I'm asking just to basically extract coefficients of powers of z and w in that identity and recover this kind of crazy explicit form of the identity. Okay. More or less, this was the form in which vertex algebras were first defined. So, yeah. Anyway, next exercise. Okay, so a slightly uncomfortable fact, I guess, is that from the Borcherd's identity, you can deduce that this function C has to satisfy this cocycle condition. On the other hand, it wasn't very evident directly from the argument involving locality that it should satisfy this condition, but somehow it does have to. So discuss. Okay, so next, I want to talk about somehow what these lattice vertex algebras look like in some sense. So first, let me recall the grading that comes from this conformal weight grading that I mentioned last time. So remember that initially we saw if you take the normally ordered product of h with h and divide by 2, that's a Virasoro element. So in this more general case, what we should do is okay, so we take an orthonormal basis for our space H. and take the sum of these guys, sum like this, take normally ordered product, and the result is a Virasoro vector. By the way, being a Virasoro vector, I don't know if I ever really quite defined it. What it means is that its OPE looks like this: TL plus 2 lambda L plus potentially, so lambda cubed times some constant. In this case, the constant is dimension over 12. And the so-called central charge is whatever this number is here. So for the kind of one-dimensional Heisenberg that we already saw, we proved this relation, and we saw that the dimension is 1, so the central charge was 1. In general, the central charge is equal to the dimension of this guy. Okay, so there's a notion of conformal weight, which is the eigenvalue of a vector with respect to L0. And generalizing a calculation which I did in the last lecture, consider the conformal weight of some random monomial in the Heisenberg algebra times e to the alpha is given by half the norm of alpha plus the sum of these indices, well, negative the sum of these indices. Okay? Weight, which I'll call delta of V. So I wanted to use this notation delta for conformal weight. And we proved that if you take the conformal weight of an nth product of two elements, well, if the elements have well-defined conformal weights, then the conformal weight of their nth product is the sum minus n minus 1. Okay? That was an exercise. So in particular, maybe back here, let me say, so write V delta for the eigenspace in which L0 equals delta. Something kind of special happens when delta equals 1. So I mean, it's easy to check. The zero product apparently preserves the subspace of conformal weight 1. Rather cool theorem. That the subspace, so subject to a rather mild hypothesis on V, this subspace V1 with this operation actually becomes a Lie algebra. So we have this way of associating a Lie algebra to a vertex algebra. In general, in fact, all you have to do is quotient V1 by T of V0, and the result will be a Lie algebra. So let me quickly indicate how to prove it. So you should put n m and k equal to 0. To get associativity. So we had skew symmetry in this form, lambda brackets. Now it can be expressed in terms of fields already. So y of az, y of bz applied to A is given by e to the zt, y of A minus z applied to B. Let me write it out. So this says that B in A is given by, how's it? Okay, so just expanding it out, you find a relation between products B applied to A and A applied to B. And when you put n equals 0 and you see that you're allowed to ignore T, then you get the result. So what happens if we apply this construction to a lattice vertex algebra? So something, let me say, so L is even. And some things which are not essential for the construction, but which I'm going to assume implicitly, is that the form is positive, definite, and non-degenerate. And if L is an even lattice, then what is V1 going to be? we get a copy of H. Right, so because we can either take alpha to be 0, and then we get contribution from those terms with alpha equals 0, and, well, in order to get conformal weight 1, the only thing we can do is take one term here with n equals 1. Right? Or we can take a trivial monomial on this side and a vector of norm 2. Okay? So we get these guys, where alpha lie in delta, where now there's a different delta than before, where delta is the so-called root system of the lattice L. And if the lattice is positive definite, then this is some finite set, right? So this kind of visual representation of VL Okay, so this is kind of what these lattice vertex algebras look like, right? You have this paraboloid, and so each of these vectors is an e to the alpha, and from it you can descend by applying these monomials. Okay, in V1, this is Pat here. Okay, so you can probably see where I'm going with this. Suppose we took L to be the root lattice of some finite dimensional simple Lie algebra. Then we're recovering a Lie algebra from this lattice construction, and the fact is it's going to be a simple Lie algebra, so it's in fact the Lie algebra that you began with. Okay, so this only works if the lattice is, if the Lie algebra is simply laced, right? Because we need its root lattice to be integral. But yeah, at least in this case, it recovers the simple Lie algebra by this construction. It's actually Borcherd's remark that this is probably the most uniform known construction of the simply laced simple Lie algebras, because somehow to do this construction, the only thing you need to do is find one of these cocycles, C. And you can do this in a more or less uniform way. Okay, so all this suggests that maybe there's actually a way of starting with a Lie algebra and producing a vertex algebra directly. Indeed, there is such a construction, so that's what I'll describe now. So let's take an invariant bilinear form on G. Recall right at the beginning of the first lecture, I mentioned that you can define some so-called Affinely Algebras associated to this data. Yeah, I won't repeat it because I already wrote it down. And if we now consider something very similar to a Verma module, slightly different, called the vacuum module, which I'll write down now. So we, as usual, take a one-dimensional representation for G hat plus, which is, as I'll now explain, and then induce to the whole Lie algebra. So you see that in this construction there's entered this number k, which is called the level. Okay, so you take this vector space. It's a module for G hat, So you can form some fields in which you take so you fix an element in G, take A times all powers of T. These are some operators acting on V, put them into a formal power series. These are the quantum fields in this structure. The vacuum obviously is going to be the highest weight vector. And T, well, it's basically determined by the axioms. So it's given by this condition here. This is called the universal affine vertex algebra associated to G at level K. I think it...
Your axioms would have a plus there. Is that an operator?
Oh, is that true? Did I get it backwards? It's... I figured, so T applied to this thing, I mean, the commutator has to coincide with differentiating with respect to Z, and I think that's where the minus sign comes from. Yeah. Yeah. So now let me kind of, exercise. Write it up here. Okay, so the OP relation between these generating fields is given by this formula here. So the kind of mental image that I want you to have of VKG is not this kind of paraboloidal shape, but rather like a cone or sort of pyramid. So here in degree 1, you have a copy of G. So maybe let me be very explicit and just take SL2, for example. So here you would have E, H, F. And here what I mean by E is the minus 1 product of the field E applied to the vacuum vector. So in particular, G1 is just a copy of, V1 is just a copy of G. Forgetting a notation that I've introduced, which is that x sub n is synonym for x times t to the power of n. So here I could apply e minus 1 2 times to the vacuum, and then I go 2 steps in the same direction. Or I could just apply an e minus 2 to the vacuum, which I'll omit the vacuum from these guys. But here I'd also have another vector like e minus 1, h minus 1. Etc. Okay? So clearly something you can do is just keep applying copies of e minus 1 and go along some ray starting from the vacuum vector. and the exercise is to make precise what I just said. Okay. So something kind of cool happens at very special values of this parameter k. So it's easy to show that as you let k vary over the complex numbers, say, all of these vertex algebras are non-isomorphic. So it's an infinite, even uncountable family of vertex algebras. Yeah, but cool things happen at specific values of the level. Okay. For example, how much do I want to introduce? So let G of this root space decomposition. Okay, so let's choose a triangular decomposition of this simple Lie algebra and let theta be the associated so-called highest root. So it turns out in this case that if you take this operator, e minus 1, or e theta minus 1, and apply it k plus 1 times to the vacuum vector, this is what's called a singular vector. And so what that means by definition is that all raising operators annihilate sigma, where raising means, goes up in that diagram, or in other words, decreases the conformal weight. Okay? So an exercise. Basically, it turns out, so this vector is kind of like some guy sitting here on this edge. So to check that it's a singular vector, it's actually sufficient to show that if you take the corresponding negative root vector, which would want to go one step up here, that annihilates this vector. Okay, so exercise. So explain why it's sufficient to check this and do the check.
Sorry, this depends on the choice of your binary form in G, right?
Ooh, yeah, that's a good point. Yeah, I'm picking the one where the highest weight vector has norm 2. Yeah, thanks, that's a great point. It totally depends on the choice of bilinear form. I should have commented that. Simple roots. Now assume, yeah, I'll put that. Okay, and really what I should have then said, take k to be positive integer. Okay. Okay, so now we can define an ideal in a vertex algebra in much the obvious way. So it's some subspace such that if you take any nth product between anything and an element in the ideal, then you get another element in the ideal. Now a remark. Due to skew symmetry, there's no separate notion of left versus right ideals. It's the same thing. So it's kind of, yeah, if you're familiar with PBW type arguments, it's fairly clear that if you define so-called ideal generated by this vector sigma k, it's going to be something which has a component in degree k plus 1, same degree as sigma k itself, and components below that. So somehow the highest slash lowest degree piece of this ideal generated is in degree k plus 1. you can guess what I'm going to do next is you can take quotient by an ideal and define so-called quotient vertex algebra. So when you do this quotient, so obviously the part generated by sigma k is not everything in degree k plus 1, it's some subspace there. So when you take the quotient, there's still some stuff left over. So sigma k would have been here. But now you get something which is kind of straight down to one vector before that, and then continues on a steeper gradient. And something quite non-obvious, but if you look at the envelope, or so the collection of all weights that appear in this quotient, it kind of continues in this way. It gets steeper and steeper. Indeed, the envelope here is this kind of vaguely paraboloidal shape. Okay, so the next thing I'm going to say is probably clear. Oh yeah, I should, it turns out, so this follows from formula 10.4.6 in Katz's book, Infinite Dimensional Lie Algebras, that LKG is simple. So simple means what? It means it has no non-trivial ideals, which is equivalent to showing that the maximal G hat submodule is generated by this vector sigma k, and that is proved in that book. The theorem so this is Frenkel, Katz, Segal. Simple and simply laced with root lattice L, then the lattice vertex algebra associated to L is really the same as the level 1 affine vertex algebra. But you see, by letting k be other positive integers, we get this highly non-trivial class of other vertex algebras, which I really don't have any description in terms of, or don't have any direct description in terms of the lattice. So some remarks. Okay, so we had a conformal vector in the lattice vertex algebra, and I've been implicitly using a conformal vector to get a grading in VK of G as well, but I haven't said what the conformal vector is. So I didn't really need it for the explanation. But the construction is given by this guy Sugawara, and it's the following formula. So pick orthonormal basis. No, sorry. Pick. Yeah, why not? Semi-simple, but I don't know, just to save time, let me say simple. So the Joule-Coxeter number of G defined by one half of the eigenvalue of omega, where omega which is this Casimir element in the center of the universal enveloping algebra. Okay, so that's the definition of this number, H check. So now Sugawara vector is 2 times so you do a similar thing to the construction of omega. You take square, but now square means normally ordered square, sum, and it turns out you have to kind of normalize by this factor, and the result is a Virasoro vector. And the central charge, C here, is given by the following formula. Involves the dimension of the Lie algebra, H check, and also the level. So there's this detail that this isomorphism is not just an isomorphism of vertex algebras, but of conformal vertex algebras. That is, the isomorphism matches up these 2 Virasoro vectors as well, which has interesting consequences. So this means so here, if we, in this formula, we take level equal to 1. So we have central charge given on one side by the dimension of G over 1 plus h check. But we already knew that the central charge on the other side was rank. Okay, and this, it turns out, is a true formula for simply laced Lie algebras. So for example, G is E7. You have 133 is the dimension. H check plus 1 is 19, rank is 7, and indeed 133 is 7 times 19. Yes, H check was the dual Coxeter number. There's this other thing called the Coxeter number, which is equal to the order of any product of all the simple reflections in W, the Weil group. Does anyone know why? So I'm kind of at a loss of what to do. So I wanted to have 30 minutes to do the last part of the talk, but I only have 10 minutes. So I think what I can do is, and the title of the talk involves a Joules algebra. So I think what I'll do is I'll define the Joules algebra. I won't say nearly as much as I intended to say about it, but at least I can give the definition, tell you that there's this important algebra, and I don't know, I'll post the notes later, and anyone that wants to know can ask me more about it. Okay, so I haven't really said pretty much anything about representations of vertex algebras yet. And in general, it's quite a hard subject. One of the most important constructions in the subject is this associative algebra called the Joules algebra. Okay. So let me first say what kind of representations I want to talk about. In here. Okay, so again, it's a key part of the structure is this operator L0. So we know the L0 acts on V with, by eigenspaces. And if we assume that a module has the same basic structure, so it has some lowest, what's called energy eigenspace, and then goes up from there in integer steps, then we'll call it a positive energy V module. So this lowest energy is quite important in the theory. It's called the conformal dimension of the module. So for any element in the vertex algebra, we have this important observation that there's a particular mode which preserves the graded pieces of any module, right? So we get that the graded pieces are preserved by this particular mode A sub 0. So the idea somehow is you look at the so-called lowest piece. Yeah, unfortunately, it's the highest piece in the way that I'm drawing these diagrams. But you give this the name M lowest. And you observe that these zero modes map this piece into itself. And any positive mode must act by zero, right? Because there's nothing lower that it could go to. So you rewrite Borcherd's identity in terms of these modes, and then you do the following thing. Sorry? Oh, yeah. Yeah. by kind of staring at the form of Borch's identity in this new conformal grading, you notice that you can choose values of m, k, and n, numbers, so that everything on this side vanishes if x is in this lowest degree piece. And what you discover is that doing a similar thing with a slightly different choice of these numbers, we can cook up some way of combining A and B so that its zero mode acts by just A0, B0. Oh, yeah. Yeah, so the key point is, yeah. So Zhu didn't call this thing Zhu of V, he called it A of V, but now I call it Zhu of V. Is now the quotient by the subspace. Turns out really amazingly, J is an ideal for this funny product. The quotient is an associative algebra. Which is given just by letting an element act by the zero mode. So you have a way of getting modules over this associative algebra from modules over the vertex algebra, sorry, positive energy modules over the vertex algebra. So if we do this process for irreducible modules, it's easy to check that the result are irreducible left Zhu V modules. And in fact, this is a bijection. So really, this algebra does far more than you would ever have imagined such a construction will do. It really knows all the irreducible modules for the vertex algebra, irreducible positive energy modules, with essentially no assumptions on the vertex algebra. So it's a very powerful tool, but I've gone over time already, so I'll stop there. Okay. questions? Yeah.
We discussed about the two-sided idea last week, and when we tried to write a proof, apparently it was necessary to assume that T preserves I. So I was wondering if it is necessary or
But I think, so because T, TA is given by, so this is a fact, theorem / exercise. So I think if this is true, then, so if A is an element in your ideal, then by definition, this term has to be in your ideal, and so TA is in the ideal. Yeah, so indeed, yeah. Okay, other questions? All right. Yes, as I say, like I've got these notes, I'll put them on the website or somewhere. I should probably clean them up a bit first. I have some supplementary notes as well, because I prepared far more than I really needed. So I have some notes on so I commented at some point that it's rather difficult to kind of get started in this theory of modules. Like if you want to show really that, kind of characterize the modules for VK of G, for example. So I prepared some notes on this kind of stuff. And it involves like completions of topological algebras and things like this. And something I thought was a nice exercise for computing OPEs is this topic of Wakamoto modules, but I just didn't have time to talk about it.